Dear colleagues, I am Frantisek Wald from Czech Technical University in Prague, and I would like to introduce you to our work, which is related to strain design limit for hollow section joints. The work was prepared by my colleagues Matias Kozich and Petr Jehlika from Czech Technical University in Prague, by Xiao and Jeffrey Parker from University of Toronto and Jaromir Kabelac from Brno University of Technology. The motivation of our work is to unify design resistance of hollow section joints with open section joints and with current finite element modeling. I would like to introduce you to the question. I would like to show you the application to rectangular hollow section joints, and I would like to show you the application to circular hollow section. And I would like to summarize this contribution. The introduction. Design resistance of hollow section joints is currently derived by failure mode method, which is curve fitting procedure. The derived parameters are on analytical models. It's also used component method, but component method is the failure is taken from the failure mode method, or from which is curve fitting. And of course we have finite element method. Currently we have two options. We have numerical simulation. This is research oriented. This is like numerical experiments. And we have numerical design calculations, which is design oriented and which is used for currently in everyday praxis. So the resistance of hollow section joints is like for other joints, derived experimentally by physical experiments, which are nowadays used for validation of advanced models of finite elements, numerical models, and they are used for sensitivity study and for limits of curve fitting procedures. How we derive the resistance by curve fitting procedure? Currently we are using the deformation limit, and the deformation limit is used in SciDec publications in ISO standard from 2013, and it's used in Eurocode for connections in preparation. But this, the procedure was not used in the previous standard. So so on the graph, if I have a deformation force diagram, I may have a deformation limit, and of course if I have some stability failure or failure before reaching this limit, we are taking the maximum. Curve fitting procedure is described as a deformation limit 3% for width of rectangular section chord or 3% of diameter of circular section chord. Of course, also this peak and it's based on work from 80s, and it's well established. On the other hand, we are using often strain limits in finite element analysis, and so our proposal is to use the strain limit because all the numerical, all the physical experiments are equipped by numerical experiments, and strain limit is important value for resistance or maximum peak load, of course. Terminology, it is 5% maximum principal strain, and of course it's important to discuss at which place, at which position. So we are recommending 0.5 thickness of chord in distance of 0.5 thickness of chord, and of course the peak load. The basis of this is it's already used for fatigue. For fatigue design, it's used 0.4, but the difference, as you will see, 0.4 or 0.5 of thickness of chord from the member. It's not too much. It's not changing the results. And for plated structures is this 5% strain used, and it's recommended also in old standard in your code for plated structure, and if in a new standard in your code for finite element design of steel structures. And it's not nothing special. On the how it looks like. So I would like to show you two examples, and one is for rectangular section joint. First, of course, if I have a finite element model, I need to validate it against experiment. So we use very famous, very well-known experiment by Fan and Parker from 2017. It's 16 experiments. It's a relatively large set. And here for beta 0.5, that means ratio between the chord and member. And here you see the working diagram, load against connection, and you see here this 3% displacement, and in red line is our finite element model. On the opposites, we have if it's loaded in compression, you have here where we are with the proposal. Here is the study of distance from the member, and here it's the member loaded in tension, and it is beta is 0.5, and here you see the limit, 3% limit is almost the same, like almost the same if you place it in different direction. If we may summarize it, of course, I took the example 0.5, so the extremes are on the limits of application, but generally it's not so big. For circular hollow section, we take plate to circular hollow section joints because we do experiments at our university, and we have nice experiment also from Toronto, from our colleagues. And here you see at 3% deformation limit what is the difference to calculate. You may see here. So we were comparing also numerical experiment from Toronto to numerical experiment by us, and you see the description of the behavior. Now where we are where we are in this study. So here you see strain limit and distance. So here you see and also here it is show that the difference in resistance is not so high. I would like to summarize my presentation. The change for 5% strain will bring higher safety in design, consistency in design, and of course a bit different values of resistances. Thank you for your attention.